So first, let's go with some definitions and concepts. And visualization is an area of research, right? So there is no one clear definition. There is a lot of competing definitions. So for now, we will start with why should we visualize stuff? And the short answer is because we are, as humans, we are not very good at seeing a lot of data, at inspecting a lot of numbers and letters and characters and rows, and we are better at seeing images of that. So it's easier in this example. For example, this is the Wikipedia, and those are two different representations of editing history in Wikipedia. And yeah, it's easier for us to inspect and look for patterns and information from that kind of displays than from this kind of representations. So basically, what we do when we create visualizations is we create visual tools. We create these visual tools to extract information and ultimately to gain insight from the data that it is representing. So for now, we will say that visualization is the visual representation of complex information. And it is good for mainly two things. One is to interrogate the data, to find things in it, to navigate and find stuff inside it, find information. And the other one is to communicate results. So I'm going to give you an example of both things at the same time. In 1854, there was a cholera outbreak. Do you know who this guy is? Well, Jonas knows. In 1854, there was a cholera outbreak in London. It was a massive outbreak. It killed 616 people, a lot. And you have to, and at the time, cholera was thought to be transmitted through air, right? We didn't know about germs and that, so there were theories, but it was thought that it was transmitted through this thick, polluted air that they called miasmas. And so you have to remember that London was back then very well overcrowded, and especially in some districts there was this. It was not. It didn't have good sanitation installations, right? Infrastructures. So there was a lot of pollution produced by people, and well, diseases generally find good ways to expand in this. So Dr. Snow had the theory that that cholera was transmitted not through air but through water, and at the time he faced a strong opposition and criticism to his hypothesis from the academic establishment, right? Because the dominant theory was that it was transmitted through air. So to test his hypothesis, he went and made an experiment. He went to a central district in London, in Broad Street, and he collected data from the people that died from cholera. So this is an extract of his map. This is the area of, this is Broad Street, and the area that he mapped. And he drew small strokes. I don't know if you can see it, but these are small strokes piled up, that each one of those strokes represent one casualty, one death from cholera. And he also mapped water pumps, right? And you have this one here. You have the black dots are water pumps. I think there's another one in this map. You have another one here and another one here. And he saw that most of the deaths clustered around this pump in Broad Street. And so yeah, he observed that the deaths clustered around the pump, and it was later known that the infection in this area in particular came from the leaking of old cesspit that was dug near the actual water well, right? So there was a leaking, and some family threw up some diapers of a baby that had, a kid that had cholera, and infected the whole water supply for the pump. And also an outlier proved the point, because there was this lady that lived abroad that went every day to that pump because she preferred the taste of that water, and she's died as well. So soon after John Snow, he pressed and published this. and the water pump was closed and closed down, and soon the infection, well, stopped. So this visualization helped Snow, on one hand, to explore the data, actually, to see and interrogate it and see what patterns could he find, but also to communicate it to the authorities so they can bring measures, right? And he is now remembered and honored where the old pump was, in Broad Street, with a plaque, and of course this is London with a pub. And this is not the first example of data visualization, but it's one that had one of the first that had actual impact over people's lives, right, or over real life. And it is also an example of these two main reasons to build visualizations, which are exploration and communication. So on one hand, we have, so exploration is a tool, a means to make questions about our data, and communication can be convey results, but also to explain things. So in the exploration part, you have graphs that you might or might not do. I'm not sure if you construct visualizations very often in your work, but those can be the typical ones: bar charts, pie charts, scatter plots, traces, things that you do to when you are exploring the data, exploratory part before you go on and build the communication means, which can be posters, papers, slides, and so on. So this is another example of visualization, which is a clear and elegant display of the introduction of vaccines over disease, in this case measles. Each of these small squares is one state, and 1 year is the average for a state in the United States, and the color is the number of cases per 100,000 inhabitants. So yeah, you can, and it's also very important in this graph, the line of reference, right? It is marking, it is because this chart is meant to communicate something clear. It has a message, it has an agenda. It's to show the relation between the introduction of the vaccine and the drop in number of cases of measles in this case. This is another two examples of the same, the same, to say that the same data set can say different things. This was done by people at Visliv, and they mapped not states, but the weeks of the year from 1 to 52, and the years. And you can not only see that the introduction of the vaccine influenced the drop in the disease, but also that the measles is very seasonal. It proliferates more in the cold months of the year, in winter, and then recedes in summer. And this is a good example of exploratory visualization because it can lead you to make more questions. Like, for instance, you could also go out and plot the differences in weeks by state to see if the differences in temperature between states also affect the impact of measles, right? Affected before vaccination was introduced. And the other one is comparative. This is just 4 examples. This one is actually longer. It's done for more diseases. We have polio, hepatitis A, and rubeola, but there are also more. And this was done because one case doesn't, a correlation of one case doesn't imply causality, right? So you could say that measles in this case stopped not by the vaccination, but also because sanitary conditions improved in that year around the States. So if you plot some other cases, you can see that if they have the same impact, even if they happen in different years, then you are after something. So now that we have an idea of why we visualize, I'm sure you have heard from these 3 terms. They're actually a bit confusing because every textbook or source that you consult will have a different definition of this. So I will give you my own, and then when you research on your own for others, well, you can compare. Basically, visualization alone is our umbrella term, and it's taken from Alberto Cairo, which is one of the reference figures in the field of information visualization. And we say that visualization are visual displays of information, right? Then data visualizations are displays of data designed to enable analysis, exploration, and discovery, which is this exploratory part of building visualizations that I talked to you about before. And mainly, they don't have a predefined message, right? In this case, you have a more or less clear correlation between the number of people who died drowned in a pool, and the number of films that Nicolas Cage made in that year. So you might believe it or not, and for that you can make more questions based on the data that you're seeing, right? And if you like this kind of spurious correlations, there are a lot, like number of lawyers in the United States versus people who hang themselves, or cheddar cheese consumption versus electrocution, and things like that, that correlate nicely in spurious correlations. But the thing is, these are tools that to allow people to make their own conclusions, right, to inspect the data. Then we have information visualization that can refer also to data visualization. It can contain data visualizations, but it's like more, it's wider than that, because it can have representations of information that are not necessarily the quantitative data. For instance, this is a map of Topkapi, which is a palace in Istanbul in Turkey, and shows a predefined route that visitors can make, and highlights the treasures that you might find in the circuit. And you can also have maps like the metro map of Barcelona, which are displays of information as well. And finally, we have scientific visualization, which refers specifically to visualization of scientific data. Scientific data that can be medical imagery, like fMRI, like the last image that we saw, but also geographical data, like weather simulations, meteorological simulations, or simulations of physical phenomena. It mainly refers to 3D data, but you can find that some texts include visualizations of mathematical, of math, or even visualizations of algorithms, how algorithms work. So, yeah, but there are more things. We are not going to work with them today, and I don't think you are going either, but just so you know, there are other types of displays of information, of visualizations. One is infographics. We are very familiar with this because newspapers and TV are filled with them. And these are multi-section visual representations of information that intend to communicate one or more specific messages. Like, for instance, this one is a diagram of how a skate field is built, like the composition of the layers and everything. So if you were curious about this is the answer to you. And the other one is how referees work. You see there is no data here, but it might contain data. You can see infographics that may contain, for instance, maps to support the main ideas, right, choroplets. There is also data art. This is weather baskets. It's made by an artist in the US that went out every morning at around 6 a.m. and recorded and observed the weather, and then built some algorithms to convert that recordings to something, and somehow it ended up in having the shape of this basket. So there is no a mapping, a scale here. The nodes and all the elements that conform the basket are actual phenomena that she observed, right, on the weather. But this is not visualization of actual information. So these are not clouds, or these does not represent actual pieces of information. It's just art. The same, well, not the same, but in the same line, you have these maps of flights in the US from Aaron Koblin, which this is an image of a video, a longer video that shows the trajectories of planes in the US for one complete day, since the morning to since 12 to 12. And it's very nice, but it's not really so rich in information, right? You don't have the color scale, doesn't mean anything. It's just the aggregation of flights over each other. So when you have an overlapping, the lines start to turn brighter. Sorry. But again, you don't have much information apart from just frequency, like which zones are more connected. And you also have data food. This is a display of the proportion of women in academia in 3 countries, Japan, Belgium, and Turkey. And this is more like an experiment. I mean, it has more information actually than the weather baskets and the map of the planes, because you have proportions mapped in, I think it's the area, I'm not sure, or the diameter of the circles. And you also have these things that are made. This is wakame salad with ginger for Japan. You have beer and chicory for Belgium, and you have these ingredients that match the country. And finally, you have physicalizations of data. This was made by the Domestic Data Streamers, which is a collective based here in Barcelona. And they put this in a square, public square in Barcelona, and asked the visitors that went to the square to grab one piece of string according to their origin, whether they were locals from Asia or the rest of the world, and start following the path according to their demographics. Gender, the floor in which they live, the age, average amount of hours that they work. Actually, this wasn't done in Barcelona. Well, so this might look like more like art than visualization, but this and the food are actually experiments that deal with questions that are relevant to visualization, because one of them is how we perceive visualizations, and how can we enhance the perception of visualization, how can we understand better. And there is one possibility is that we can understand things better if we can touch them than if we just see them in the screen of a computer, right? So these people deal with this kind of questions. So what is a good visualization? How do we improve them? First, let's take a look. This is a diagram of a typical pipeline of doing visualization. You have the data part, where you gather and collect the data, the processing, where you may filter and clean up your data and so on, do some processing. And then you have the loop of the visualization itself, in which you encode, you choose how are you going to map your data to visual attributes. And you have to remember that here you have a human user in the loop. So the human user needs to perform a specific task that constrains the encoding that we are going to use. This is shown a bit clearer in 2 parts in this other diagram, where you have also the data part, the data acquisition and data processing. But the part of the visual of the human user is split in 2, graphic design and human-computer interaction, which is when you make interactive visualizations, like browser-based or actual software. So we are going to deal only with the graphic design part in this class. What are the mechanisms that make that visualization are easily perceived by our users? Okay. So we tend, especially people that outside from the area, tend to think that design is only the art of making beautiful displays, right? But and it deals only with aesthetics. But in part it is, it deals with aesthetics and beauty. But that's only one part of it. Design is also about effective communication. It's also about, it has a purpose, it has a function. It has to deliver a message. So these designs, for instance, might be aesthetic or beautiful, because aesthetics and beauty are subjective attributes, right? It vary according to who is looking. But there is something wrong with them, right? They are not passing the right message at all. I mean, you are at least, if you're not advertising pornographic cable TV, this is clearly passing the wrong message. This is not advertising your antenna shop properly, right? So, and this happens with design in general, not only with graphic design, because it's more or less the same thing. I mean, design is not art. One of my my favorite actually quote of the difference between design and art is from Donald Judd, an American artist, that says that design has to work, art doesn't. So if design has a function, well, these designs and the previous ones clearly are failing in delivering this messaging, fulfilling their purpose. So in graphic design, the primary function, well, here it is clear that which is the primary function. In graphic design, the primary function is to convey information, right, specific information. There is also a quite modern approach, which is active vision, and it has to do with graphic design, but it's a new understanding of human perception that is based on the premise that seeing is understanding. So it makes sense because of what we know now about the mind, which is not much, but it's something, is well, we have almost half of the brain devoted to vision, right? And when someone is explaining something to you, and you finally get it, you don't say, oh, I smell. You say, oh, I see, because seeing and understanding are very tightly close concepts, things that happen in our mind. They are closely related. So, yeah, based on the importance that vision has on thinking, active visualization puts perception at the center of design. Right? It's what they say, what they call designing with the mind in mind, having into consideration how we perceive, how we visually perceive, to make designs that can fulfill their purpose easier. So yeah, so for instance, human memory is not very reliable, right? We tend to forget things, and as we get old, we can even completely fabricate memories, things that never happened, and we think that we remember, but they didn't. And sometimes we remember things that are completely useless instead of what we want to remember. So we have built these external hard drives for our memory, which are books and logs, right? They are external memories, external aids for our memory. So active vision says that we can do the same for understanding, which is to build these cognitive tools, which are designs, to help us understand, external aids for thinking. But yeah, perception is quite a complex phenomena, and cognition is well, even more, because the mechanisms at work in our minds to process the world can sometimes distort the viewing, our understanding of it, right? We will see some mind tricks later. So active vision is about understanding how we think visually and use this to make these thinking tools that work better. And this is especially important in data visualization because cognitive tasks can be particularly complex, right? More demanding than other kinds of graphic designs. So, for instance, understanding active vision can tell us, if you look here, what colors stand out over the others, so we can plan our visualizations to highlight certain information over some other. Or we can know how we perceive differences in size or contrast, also in size but also in color, to organize and arrange information in our page, in our display of information. So that's what we are going to see next. So we are going to see a little bit of visual perception, and then we will see a little bit of graphic design, considering what we see here. So we used to think that this is not going to be very deep, right? Just a couple of concepts, so we can talk about how to make our visualizations better. We used to think that we could perceive the whole world, right? That we had two cameras here that perceive the whole world at the time, at any given moment, and then a perfect picture went to the back of the brain and it was processed there. But we know that we don't. So we have, for instance, this is a plot of the resolution of the fovea, and we have extremely high resolution at the center. But as we go towards the outer part of it, there is much less resolution. So we can only see in detail at a very narrow point of our eyes. What happens? So the reason why you can see me and the screen at the same time is because we make these very rapid eye movements called saccades, and they are faster than thought. Literally, they are very, very fast. So the impression that we get in our brains is that we are seeing actually everything, the complete frame at any given time. So the result is that we have almost immediate access to external information, and the lag is so small that we perceive it as no lag at all. So the information from these 100 million receptors in the eye is compressed in these 1 million fibers of the optic nerve and sent to the back of the brain, to the visual cortex, where it passes through these zones that are called V1, V2, is visual cortex zones 1 and 2, where billions of neurons process the image and extract patterns, and mostly they extract patterns and are used to plan future actions, like another eye movement or movement of motor responses. And in V1, this is the part that interests us now. It's where it takes place the extraction of what is called low-level features, which are color differences or elements of movement or form that we can perceive before others. Because from there, the information goes to other zones of the brain, where they are assigned with context or patterns, and you have face recognition and things like that. But there are some attributes that are processed before than others. Yes. So this is only to say that some things happen earlier in the brain than others. So that's why you can see the red dot down there even before I say anything, because it catches your eye. That's the reason is because this is one of the low-level features that are processed earlier than other things, than context, for instance. Right. So we know that some actions are like hardwired in the brain, and other, like those ones, respond to more learned skills. I mean, this is also intuitive. You will go to the X to close, but this has to do more with learning and culture than with the hardwired low-level attributes. So I'm going to show you a video, and you have to tell me how many passes does the team in white clothes make. I think there's no audio here. No. No, this.
The answer is 13. But did you see the moonwalking bear?
Did you? Yeah, it's amazing. Gets me every time. I'm going to show you another one. This has to do with what we were talking about, right? We can focus on one point, and if we are focusing on that, we exclude the information that doesn't help us in fulfilling the task that we are performing at the moment. Now look at this one, makes you feel even worse.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, son.
I was planting my petunias in the potting shed. Constable, arrest Lady Smythe. But how did you know? Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you?
Did you see 21? No.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts and precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, son.
Well, I was planting my petunias in the potting shed. Constable, arrest Lady Smythe.
So we are not going to deal with memory tricks. We are going to deal with the mind tricks of visual perception, specifically those that have to do with static images. So for that, well, it's because we don't see the world as it is, because there is a major processing happening not only in the brain but also in the nerves that transport the information and the receptors, the eyes in this case. Because of this major processing of information, the mind can play us some tricks, as you saw just now, sometimes. So understand this, how these tricks work can help us to make better designs, if we take them into consideration. We are going to see the Gestalt principles and some attributes that are called pop-out, grouping, and salience or contrast, which are very, very useful in doing design, especially information design. So Gestalt is the oldest one of this. It is Gestalt psychology is a school of psychology of the early 1900s. Are you familiar with it? Good. So basically they did some experimental testing, and at the time psychology was struggling to become a real science, and it came from previous currents that regarded the mind as a black box that we shouldn't consider and understand. So they made these experimental studies showing images to people, basically, to study the mechanisms of visual perception. And they found that we don't see the world, the things as they are, but there is this processing happening somewhere in the mind, right? Yeah, and our mind does so. For instance, here there are 3 Pac-Man characters facing each other, but we all see a white triangle in the middle, right? That's because our mind tends to impose meaning over what we see. The same in the cup over there, we will surely see 2 faces facing each other, and we see closed brackets because of this is the name of the principles that they studied. proximity, similarity, continuity, and none of those attributes are actual properties of the object. That's what they say, but properties that we attribute to the objects. They are not inherent to the objects. It's something that happens inside our minds. This is why we can see a funny face there when there are only a couple of lines and 2 circles. And it's the same way that the closed brackets work. So there are many other principles, but some of the other principles consider motion. For instance, one of the tests that they made was to find the persistence of vision, which is actually the reason why films work, right? We see 24 or 25 or 30 frames cut images in a sequence, and our minds can reconstruct movement when there is no motion at all. So we're not going to deal with motion, Gestalt principles, only with those that deal with the static images. It's the same reason why, yeah, you remember the logo of before? This is 2 dancers, by the way. This is one male dancer and a female dancer. But you can see something else if the Gestalt principles act. In the other image, you have a vase with 9 dolphins. Can you see them? One dolphin here, one dolphin here, one here, one here, one here, one here. 9 of them. It said that this depends on culture. That if you show this to a little kid, well, they would see the dolphins most likely. But we did an experiment with the son of my boss, and he saw a couple of a man and a woman being nice to each other. So I don't know about that. So Gestalt principles, the ones that we just saw, apply to design. You can see how proximity, for instance, help us structuring numbers to create groups of numbers. Closure creates categories. Similarity creates consistency between objects in a display. Connectedness shows a relation, a hierarchy of, this is a decision tree, a very good one. Continuity helps us to follow the lines of this graph to see the relations between the nodes. Yeah, of course, we use most of these things intuitively, right, because we've learned to. But knowing this might help you to later decide what is the best way of showing your visualizations based on these principles. So grouping is a separate category because it has been elaborated further to have to be various types of it. You have grouping by connection, by containment, proximity, or similarity. And yes, this is also very important for us, not only for structuring data, but also to make posters, for instance, to structure the information, complex information, sometimes not as closely related in one display. Now, those things that we said happen at a low level of visual perception. They are low-level features, which means a very early stage of processing, which means that we can perceive them very fast, faster than other things. Like these 3 first examples are it is very easy to detect on them the different object among the others, right? Because we are very good at detecting this different orientation or difference in size or in shape. It is less obvious to distinct clustering, grouping, and it's even less obvious to distinct here. The different one is this one, to distinct slight differences in angle, in leaning. That's why this is one of the reasons why pie charts are like the Comic Sans of visualization. We will see that later. So yeah, continuing with this, that happens. We can distinguish some shapes easier than others because not all attributes or not all visual channels are as strong, are not perceived as strong by our minds. So yeah, I don't even have to say find the red dot here. It's very easy. And yeah, it doesn't take long, right? Now, if I ask you to find the red dot in the two images below, you might take a little longer, right? And even more if you have to find the red dot in these two. Have you? Good. So some channels like hue, with some channels like hue, which is the difference in what we usually refer to as color, red and blue are two different hues. With channels like that, the speed detection, the speed at which we can detect the object is independent of the count of distractors. So it doesn't matter here how many blue dots we have. We will perceive it as fast. But with other channels like shape, and this is based on experimental data as well, the speed detection is affected by the number of distractors, and even more if we have mixed channels. That's because the primary visual cortex can be tuned for circles or for red things. But tuning it for both, well, it's more difficult. So we have to make a conscious effort and take more time to process it to find the red dot in the last two cases. So we owe this pop-out to Anne Trishman, which was a psychologist. And she made these experiments to identify the more salient channels and got these results of the dependency or independency of number of distractors. To identify the channels that are more salient. Yeah, they find this combination of target and distractors and the dependency between them. So this was used to be called pre-attentive attributes. You might know this by that name, but it's not longer widely used because our understanding of attention has shifted. So we know that this takes a lot of attention, but it doesn't need to be a conscious one, right? Yeah, so we can say that based on the attributes of the objects, they pop out from the environment, which is the same that happens in any kind of image, right? You have, depending on the characteristics of the distractors, identifying something can be easier or more difficult. Have you found the guy with the goatee? Yeah, it's over here. And this is not only, pop-out is not only a characteristic of the object itself, but is highly dependent on the surroundings. So this is called contrast. The same happens here. It is very easy, by contrast, to find this one, but it's very difficult to find this one. And I can't find it. It's around here somewhere. It's because they are too similar. So in terms of pop-out, contrast refers to the basic features that are processed in the primary visual cortex and that can be seen in a single eye fixation, which is less than 1/10 of a second. That's how pop-out is defined. And the simple features that lead to contrast are color, orientation, size, motion, and stereo depth. As you can see some here. And the lesson for design of this, well, is very straightforward. If you want something to be easy to find, if you want some part of your visualization that supports your message more strong to pop out over the rest, then you can use differences in hue or differences in size or in shape, right? So your audience can go straight to it. Or even better, you can combine channels. You can use size and color, like in this example, and not only one, to reinforce that the effect. Am I going okay? Too fast? Slow? If you have any questions, just raise your hands. So let's have a word about color now. And we will start with color perception. So very basically, again, we don't have cameras. We have eyes, and the eyes have these three types of cells, of cones, sorry, that perceive low, mid, and high frequencies, which translate to red, green, and blue colors. And we also have the rods, but we don't use them as much today because they work for low light environments, and there is no low light environment in modern life in our cities. And they are also not relevant in design. So this is how a camera array would see, with equal intensity for the three wavelengths. And this is how human eye sees. Our cones are not excited in the same degree by the different wavelengths. So long frequencies generate stronger stimuli, and they also inhibit or excite each other, which has an effect. There is this theory called the opponent process theory of color, of how we process color. And it's widely accepted now. There are others, but this is what I assume to be more valid. So basically, the brain combines the signals by subtraction or addition, right? You can see here that the long and medium, red and green, are added to create this luminance channel, which is from bright to dark. You have subtraction from between blue and red to create red and green to create a red-green different signal channel, and you have from the result a subtraction of the yellow and blue to create a blue-yellow difference signal channel. So the result of this is that if you have these additions or subtractions of signals in the cells, you have colors that see brighter because there are more cells acting there. So that's why there is no such thing as a dark yellow, right? Yellow is always bright because it's the sum of all this excitement in the cells. And this is why we perceive some colors as being brighter as others. This is a desaturation of a rainbow color scale. How many of you work with color scales in your plots? None? Okay, 2, 3, okay. Well, depending on the branch you might need or not to work. Well, I asked because many programs of scientific visualization especially have this as a default, and I have 30 slides that I took out of these presentations about why this is a very poor default. And short story is because of this, because it is not equally distributed. It doesn't show continuous increase in values, and mapping this to a continuous increase in your data, a value in your data, well, may lead to mistakes in the interpretation of your data, right, in the visualization. So it's not perceptually accurate. Now, the properties of color. Color is a mix of things. When we say color, usually we are referring to this, which is the hues. But we also have contrast, saturation, and lightness. In contrast, well, the visual system is better at perceiving differences between patches of light than actual amount of light, because we can tune, right, our eyes to the environment in which we are. But if we have things close to each other, this is the same gray here, but you perceive it as lighter or darker depending on the surrounding shade. Then you have hue, and you have the strongest signals of hue on the channels that we saw before. This is why these are like called primary colors and things like that. And there was this study just to show this is like a rank of the importance in which ones do we perceive stronger. There was this study that was conducted in 100 languages, and they found that in some languages they don't have names for all colors. In some of them they have only two, and those two, all languages have words for these two. The languages that have a word for a third color is always red. The fourth varies between, I think it was green and yellow, and then it was blue. So this is something that is hardwired in our brains somehow. So that's why red is such a powerful color. Then you have saturation, which is the vividity of the color, the strongest signal on one or both of the chromatic channels. And then you have luminance, which is luminance is the measured amount of light, the brightness. Brightness is emitted light. Luminance is the measured amount of light, and lightness is refers to the surface color. They are different concepts. So colors depend on their surroundings, and some properties influence each other. Right? If you see, it's a similar phenomenon as what happens here, is that these two blocks here are exactly the same shade of gray. But if you don't see this ladder here, it is impossible to see it. And this happens with hue as well. You have on one side a contrast between hues, the proximity of opposing hues. Remember that we said that there was a blue-yellow difference channel, a green-red difference channel. If you juxtapose opposing hues, then you create stronger contrast effects. Also, saturation changes with luminance. So bigger or smaller ranges in less or more luminance. If you have low light, then you can make smaller variations in hue. So a similar phenomenon with hues. These two colors are exactly the same orange. I actually used Photoshop to pick the colors, and they match. But you see a dark brown on the top, and you will see a bright orange on the bottom, right? And this is because of contrast. The surrounding colors affect a lot how we perceive color. So colors are not seen isolated, never. Same here. This can lead to very curious distortion effects. Because all the image is reddish, we perceive this gray, pure gray over here as being green, when it's not. And this is a very good one, but you see a green spiral here and a blue spiral here, right? Wrong. These are the same color. It's only the contrast between the lines that go outwards that make it make us perceive it as they are different, but they are not. So color is highly dependent on the surrounding colors. And it's also highly dependent on size. Right? You can see here that by size you can, it affects the way we perceive it. So we have that colors compete in terms of lightness and hue, but also in size. So as a general rule, small points that are important to the visualization should stand out from the background in some way, in both chromatically and in luminance. So you have some examples here. You have some different variations. So you have variation only in hue, and you have, this is one of the strongest difference channels, yellow versus, well, it's not actually yellow. In fact, you shouldn't use yellow. Well, it's very intuitive, right? If you use yellow over white, then you won't see anything. But using yellow against dark background is very effective if you want to highlight something. So you see again that, how easier or more difficult it is to identify objects in these variations. And this is something you can use for your visualizations, right? To control the background of your visualizations and also the color and the attributes of color of your data point. There is also, color deficiency. About 8% of men have some sort of, well, actually 8% of men have red and green color, which is deuteranopia, I think, or something like that. There are three major types of color deficiency, which is an inability to see one of the channels, basically. So you have these three: deuteranope, protanope, and tritanope. And it is, well, it's 8% is a high number, so it is a good idea to double check your visualizations with, there are a lot of simulators online. Photoshop also has a filter for different filters, actually. This is done in Photoshop to test that if you are actually choosing the right, if you are choosing colors that can be seen by people with color blindness as well. Not seen, perceived. So since not all scales are equally perceived by colorblind people, so if you care for accessibility, then you can choose scales that are perceptually tuned for this color blindness. So the last two. This last two are presets in ParaView. I don't know if you use it. It's a scientific visualization software, and I think it's in others. But it's also a library in Viridi, so you can use it if you want. These are perceptually correct color scales and are tested. So it's not only that colorblind people can use can perceive the different the changes according to the variation of in the data. We also can, as people without color deficiency can, because the variation in hue, color, and lightness of the scale is even, right? In contrast to this one, in which you don't have a clear progression of color. These ones are made to have a clear progression in color that may match the progression in data. Yep. So some tools. Viridi's colorblind simulator is Rehue. If you want to test this. So matching color to data. Some word about color scales. Yeah, we have three main kinds of color scales: sequential, divergent, and categorical. Sequential color scales, which go typically from one value to another, are very suitable to show data sets that match, that go from one value to the other evenly. Divergent color scales are good to show data sets which have a central value and values that diverge, that go from, for instance, temperature in degrees. You might have positive and negative degrees, right? So it's very good to show this difference from this departing from a middle point. And you also have categorical, which, to show different categories. And this one usually uses differences in hue, because differences in lightness and in saturation, like these other two, are we link them more easily, perceptually, so gradients are closer to how data grows evenly, right? So if you want to show that things are not really connected, then it is better to show differences in hue that are not correlative. So for instance, you have these examples of sequential data, and they are mapped. This is a color scale that goes from dark blue to white. So it is very intuitive to see that, that there is an increase or decrease in the data. That matches the increase or decrease in the lightness of the color scale. The same happens in the other one, which is ordinal and has a discrete color scale. This is the, I don't know if you can see the legend over here. So it's more or less the same. It goes from one hue to the other, but also changes the saturation, but is a discrete scale. This is another example of a sequential, continuous, and discrete scale. So this shows the ash deposits from a volcanic eruption over Europe. And we use this is a poster, a figure that we made at the visualization group of the BSc. And we used a discrete scale because we weren't as interested in showing the progression of decay of the thickness of the deposits, as much as the areas that it covered in these steps, right? Which areas had 1 centimeter of thickness, or 2 or 5, not the how fast it got thicker or shallower. And the good thing about this is that the differences are more evident, right? If you have juxtaposed different lightness, you can see the differences more easy. This is another example. This is a heat map, and this is also discrete, but there is a lot of granularity here. I don't know if you can see it. You might see it as continuous, but you have small squares here, but a lot of them. This is a divergent color scale. One, yeah, it's, I would say this is a mistake, but usually you want your 0 to match the middle color, right, the white. The same here. Unless 12 is a reference value from which in which you are interested to show the difference between lower values and higher values, you shouldn't be using a divergent color scale. You should be using progressive linear scale, like the one on the other side. Then you have the categorical scales, as I said, where you usually have the different hues to show different categories. Yeah, you can also have, like in this example, categories as colors and size to represent the amount of something. These are called donut charts. And you can also have grouped categories. So you have 3 categories, and in each category you also have a linear color scale that shows 4 different values. Sorry. So you have 4 categories for, there is a black and white at the end. 4 categories, which are 4 different hues, blues, reds, greens, and grays. And you also have 4 steps of saturation to convey this increase or decrease in a value. In this case, I think it's intention of both or something like that. And yeah, some advices to use color. So luminance and contrast is, the contrast in luminance is necessary to show detail. It's better to use perceptually linear scales like the ones I showed you at the end. It's a good idea to match the data type with the correct scale, divergent, linear, or categorical. You may want to keep in mind the color blindness, and also people who print papers. If you're going to write an article and you think that your reviewer is going to print it in black and white, then yeah, if you do things in color, you should consider how it looks when you desaturate it. So when your reviewer sees it, you are still sending the right message. Also, yeah, make missing data recognizable. That's a good example of having the background being, I don't think you can see it, but the background here, this is where there is no data, the oceans. This is only showing data inland. And this color is quite similar to these areas here. So it is a good idea to make it very different when you have where you have no measures, to make it very different to where you do. And yeah, connect color to meaning. These two are images of temperature on the surface of Mars, if I'm not wrong. And yeah, which one do you think conveys better the idea of heat? Of very, very hot. Can you see it? Which one? The upper one. The upper one is more intuitive, yes. But so we at the group we want to do an experiment, because there is people who perceive red as being the maximum value in a heat map, but there is people who perceive white as being right, and I think this has to do with fire, where you have the red as being the hottest one. So there is no clear answer. I mean, this is the one that won because they deemed that white represented better the maximum temperature, while blue, and yeah, this is more likely, blue represents better the coldness, right? But we have, in this example that I showed you, this is a heat map that we did in the group. We did the same, yeah. White is the maximum value, and red is the minimum. But we conducted some user testing. So we interviewed users to see if we were doing things right, which is validation. It's a good thing to do with your graphs. And half of the users, I think, said that the color scale should be reversed, that red should be represent the maximum value and white the minimum. Differences in perception. So let's make, how are we going? Let me make a small pause here. Yeah, okay. Let's make a quick exercise. I want you to come here and draw representations of these two numbers. So we are going to do a little bit of data visualization. So I'm going to start with a very easy one. So you have 73 and you have 34. Now, who wants to come next? Come on. Or tell me, representations if you are shy and don't want to come here. How else can we represent these two values? Yes? Please. Yes. Very good. Size. This could be, thank you, font size, for instance, right? Any other ideas? Come on, how you represent your data usually?
With a
Pie chart, great. We have a pie chart where we have, this should be something like 34 and 73, correct? More?
Big circle for 73 and smaller.
Great. Big circle. So this could be 34, sorry. So this can be areas, but it can also be diameter, correct? So you would have different sized circles. What else?
Big square partition proportionally to the numbers.
Good. Proportions. So you would have something like this, for instance, 73 and 34. More? I'm going to do one. You can have I'm not going to do 73 of this, okay? But you can do something like this, or something you see in the newspapers usually, which is a repetition of icons. You have 30, 70, versus 34 repeated icons to represent whatever value that you are representing. What else?
Maybe 2 lines with different thicknesses.
Thicknesses, good. Just lines, like horizontal. So you would have something like this and something like this, yes? Good. More? Come on, we're missing some that you have certainly used. How else can we represent these two numbers? Writing, yes, it's not quantitative, but it makes it, yes, 70. Three and we also have coordinates, right? You have 73 and 37, for instance. You have matrices and so on. So this, anyone else has? No, okay. So this exercise is to show you that there are lots of ways to represent data, not just the obvious ones in scatter plots or bar charts, but many, many more. This exercise, the maximum that I have reached in classes like this is 14, which is not much. But some other people have reached up to 45 representations, which is quite good. So you have, pie donuts, you have height in icons, you can have color and hue, which we don't have here, and many other representations. So how we decide to use the particular channels, and well, it depends on the data that we have. Let me show, oh, sorry. Just one moment. Okay, sorry. So not all channels are equally effective to show all kinds of information equally. So there is this scale by Alberto Cairo with what are called visual channels or visual attributes. And what we do when we plot information, when we plot data, is assigning the values in our data to visual channels, right? This is what we have done here, assigning these two numbers with something, some visual channel, size, position, length, whatever. So these are some of the visual channels that we have at disposition to map our data, and they are ranked on effectiveness, more or least effective, and effectiveness being in this case the taking into consideration our ability to discern the differences, the small differences. So, for instance, the position on a common scale is very easy to perceive by us, right? So we are very good at seeing this. This is why bar charts are perhaps the most effective kinds of visualizations that exist. Then you have the differences in angle, and you have areas. We are not very good at differencing areas. We have position in 3D space, which is also bad. 3D has many problems in mapping data because a lot of things interfere there. Like, for instance, you have perspective, so you cannot use size to map a particular value because the size will vary not only with the value but with the distance to the viewer, right? So there is one less channel that you have. You also have luminance, saturation, curvature, and volume. Yeah, and this other ranking also from Cairo, that comes from another designer called Cleveland, shows this effectiveness but with two different axes. So up here we have the types of visualizations that let us make accurate estimates of difference. So again, bar charts, scatters, and line charts and things like that. We are very good at seeing small differences in them. But as we go down here, we cannot make these accurate estimates. But if we use these channels, we can make more general estimates. Like so we are not very good at seeing the slight differences in a value mapped in shading, but we can see general patterns easier in this kind of representations there. That's why maps, choropleths, maps with color scales work so well, right, to convey information, because we can see the overall patterns in the representation more easily. So yeah, let's go to design. So we said that visualizations are cognitive tools that are meant to help us think, and yeah, and to help the brain of the audience to execute a task. So yeah, let's examine this example. This is infographics based on data visualizations about casualties in Iraq from 2000, well, when the war began, 2000 I believe, to 2010 I think it is. And yeah, it's very powerful because it has this clear analogy of dripping blood, of course, and it's original because it has the inverted axis to facilitate this, right? And it also works very good because we have these other things in the middle. So we have this big red stain in the middle that catches our attention, and these graphs over here make the view gravitate towards the bottom and see this. So it is designed for us to read it in a spiral type of trajectory. So boom, 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 boom. So yeah, I don't think you can see it, but these are civilian deaths. These are deaths on the of the allies, yeah. And this is a map with casualties. And yeah, opposing to that, these people of the Florida Department of Law Enforcement made this similar chart, but they don't have as much granularity as the others, so it looks more dull, right? You don't see as dripping blood over here, you just see a red stain. But it is also misleading because they did the same of having this axis inverted. You have the 0 here and so list casualties and more casualties here, but they did some tricks inadvertently or on purpose to have the horizontal axis down here. So if you don't look carefully, you will think that in the vertical axis you have nothing here and the maximum value here. And your perception would be that, there is less people dying in Florida by guns since these nice people did this, enacted the stand your ground law. While it is the other way around. If you see the graph just inverted, the perception is obviously that the number of deaths increased, right? So yeah, this is to say that there is always a story to tell and agendas. So if you compare them, the errors here that make this visualization more misleading than this one is one, the axis, having it over here. If you're going to invert the axis, then you should do, like in this case, that you have both horizontal and vertical starting from the top, not at the bottom. But also one thing that plays in favor to this one is not having a lot of white space here. So if you have it filled with elements, you won't you will perceive it as not being part of the data, right? What we saw of mark your non-data clearly. If you see white space here, you might be confused and think that that is where the information is. Also, color has semantics. If we just change the color, then a lot of the meaning, well, just disappears. It's not only how we perceive, like the speed of perception that determines what colors can be used, but it is also the meaning that we want to give to our data. Now let's see a little bit on composition. Is there any graphic designer here? Or anyone that has made a course of graphic design? No. Okay. So how do I apply these things? We are going to see very shortly rules of grids and proportions, and basically how to arrange information in a page. So this might be useful for you to make your posters or some presentations, even slides for presentations. So grids are a tool. You can find templates online that and they are very simple and easy to use, and they are a classic way of structuring information. And remember that our eyes look for structure, right? We process information and extract patterns even when there are no patterns, because we seek for structure. So presenting information in a structured way helps the viewers to understand the message. So it is grids are, as we will see, not mandatory, but can be helpful in arranging information because they add order, continuity, and harmony. So you can have columns, you can have rows, but you can also have other types of grids to arrange information, like mosaics and full-sized images and things like that. So they are very flexible. You also have the rule of thirds. If any of you does photography, you probably know about this one. And it's basically to divide your space in 3 on both horizontal and vertical axis, and place the objects of interest in intersections. And this is supposed to give you, well, images that are more balanced or better perceived. And yeah, this is more popular actually than in information visualization in cinematography, movies, and in photography. But it's also used to a lesser degree in graphic design. You also have the golden ratio. I'm sure you have heard about this. This is a magic number that results from dividing these Fibonacci numbers by the preceding number in the series. And the ratio is then used to subdivide a rectangle and have this and end up with this Nautilus shape spiral. And yeah, it was first popularized in the 16th century, and it has been used in painting and also in modern web design, as I say. And it is supposed to drive focal attention to the important things on one. This is a painting from Dalí, by the way, and we know for sure that he used this rule of thirds to divide the page here and place these two apostles over here. But we are not sure about the next slide because, yeah, this one we are not sure. There is no evidence that Leonardo used this to paint the Gioconda. But, the claim is that we perceive this golden proportion as being more pleasant. And some call it actually the number of beauty. So, and they have tried to overimpose this pattern, like in this case, to a posteriori to justify this, that this is somewhat a natural pattern with very curious results. So whether it's not the number of beauty or not, it is one tool we have in design, right? We can use it to arrange information and see where it gets us. It's the same as with grids. It is not a science, it's more like trial and error discipline. So you try how your information looks like when it's structured over a grid or over a rule of thirds or over this golden ratio, and see what you like more. And also you make tests with peers to see what works better, which is the goal. So yeah, you have these two examples here. So besides being aesthetically pleasing, grids and these ways of structuring information help us to organize the information, to create hierarchy. To create hierarchies of elements. I mean, here is very clear, but this is not only because of the arrangement of information, but also because of the use of contrast in size, in color. But it's very clear that your eye will be posed here first and then gravitate in this direction, right? You will go from here to here, passing through here, and then end up in this small sign here. They are placed over there to drive your attention. The same with this one. You have this big display that is meant to attract the main attention, and then you have this high contrast here to make you go in this way. Of course, you might or might not look in this way, but that is the intention of the design, at least, right? To arrange information so you don't miss things, to make the viewer pass through what you want him to or she to see. So grids and guides are good tools to structure information, and they provide a solid and tested base for multiple supports, web, print, and some others. But they are flexible. We can manipulate them, right? You see those examples over there where you can place images that exceed the margins of your grids, and yeah, it's not a big deal. And you can ultimately break the grid, right? Pass through it. So grids are good for complex projects, like in your case posters, and I don't see them as being very useful for a single figure in a paper. But if you're going to tell a story in using multiple displays, then it might be a good idea to use this. Yeah, same here. This is an example, a case study of a poster that we did. And this is a research of one of our colleagues at the BSc that made simulations of volcanic ash dispersion. And he published it in Nature Reports. But we also made this poster for this infographics to explain the research to be in the newspaper. So it was a very different approach. And we used a similar design. We have a page divided in three where we have a central image and a title that is supposed to catch your attention and make you pass through the small visualization on the top and then go to the bottom to gain more detail. So you have the main message of your visualization where user can see it, and then you put the smaller bits of information that help support the message on sides or at the bottom and other places, making sure that you put small signs, points of interest to drive the eye towards these points. I'm running out of time here, so I think I'm going to give you some words on typography. Good? And then we will just finish. So I choose this image, which is alchemy, because typography is this kind of dark and mysterious art. I mean, a craft. There is no clear, there are recipes. There is no clear knowledge about how it works or doesn't work. I mean, if you talk to people who make typographies or use typographies, they won't really tell you much about how it works, how what works best or not. And we know that some things work, but we don't fully understand why. And there is no work done like the one on perception that we saw, right? Perceptual studies to understand how typography works yet. So not that I'm aware of. And yeah, it would be very good to see it. So a wrong choice of a typeface can have dramatic results. Are you Catalan? Okay. So a wrong choice of this small thing here is the difference in this word between shit and food. So if you have a restaurant and are advertising something, you and there is this huge difference, you should make sure that you choose a typeface, a font that has this very clearly marked, right? And it can be even worse. I mean, there are very dramatic examples of how a wrongly chosen typography can affect the message that you are delivering. So, there are some formal aspects that we are going to see about typefaces, but it also depends on, heavily depends on taste and conventions, what typefaces we use and which ones we don't use. So, and conventions and tastes change over time. So what the following things that I'm going to tell you are current common practice today, but they are not like stone-carved rules. So it might even happen that we use Comic Sans in 20 years, like we use Helvetica today, who knows. So you have two main families of typefaces. You have serif and sans serif. Serif is this small appendix that some letters have, and it's usually serif letters usually work best for long texts. You will see it in mostly on books, novels, and such, because it's supposed to help to create this path to guide the eye, right? So it's easier to read long text. It's supposed to be easier to read long text with serif in serif typefaces than without. And sans serif works very good for titles because they are very clean and elegant. But also keep in mind that typefaces are voices. Like we cannot shout when we write, so the typeface that you choose is the way in which you are delivering the message, how you are saying it. And it affects the message that is delivered. So it's not, these are Perpetua, American Typewriter, and Avenir Next. It's not always obvious to know what message you are sending, but at least you can try to know what message you don't want to send. So do you want a typeface that looks more modern, that looks sophisticated, or that looks old or classic, or so you can make choices around that. So one general rule is that don't combine in the same display more than 2 fonts, because it looks confusing. And if you're going to mix 2 fonts, it is better to mix serif with sans serif, because it creates more contrast, then the difference is easier perceived and creates more pleasant results. That's the theory. In this chart you have serif here and sans serif for the small insets. So serif is for the title and the main explanation, and sans serif is for the insets, which also have a more condensed type. So you can read better this, so you are engaged into the visualization, and then if you go for more detail, then you have to work your way through this smaller text and more condensed text. Also a good practice, this is modern retype. What designers say, that is better to align left than justify. Actually, justify is not very good, because you completely break up the kerning and spacing between words, and it becomes less pleasant to read long texts when you have these gaps in the middle. Yes, so it is a good idea to not alter to not mess up with the spaces between words, because designing a font is a very long process. One stage after the design of the type is called the pair trials, where each letter is placed on a side with all the others to see how they work together, and they are tuned tuned to look better. And they also test the white spaces between the words. So if you mess with that, you are modifying the original character of the typeface. So the other thing is kerning, which is the space between letters in the same word. And it is also not a good idea to mess with that, because then your megaflix store can be read differently. So usually in text editors you don't have the option to modify the kerning, but if you do, don't. Save other alignments, like central alignments for titles. So it's better to justify left for long titles, and use different ones for titles and subtitles. This is a recommendation of how long mass aligned should be. Less than 28 spaces, which means characters plus white spaces altogether, is difficult to read, because you have 2 short sentences, so you have to jump lines too often. And more than 75, this is around between 65 and 75 is the recommended length for text, and more than that is too long. The spacing between lines, again, you usually don't have access to that in most text editors, but keep in mind that defaults are good in this case, because they are balanced to the typeface that you have chosen. So the spacing between lines is very dependent. You can say that a space of 6 or 7 will work for all the typefaces, because they are different. They are different sized, even at the same font size. So it's better to either keep the default or manipulate with caution. You can also create hierarchy with the size of the font that you have chosen, but also with style. It is bold, regular, italic, you can use that to create a hierarchy in your text. I mean, you do. When you write articles, you are using this in title, subtitle, section titles, and so on. But recommendation here is that if you are using this, a good idea is that not use too many similar weights and sizes, because then the differences won't be very clear. So it is a good practice to keep the contrast between them. Then, yeah, style. You have italic, bold, and all caps, which modulate the voice, right? Modulate how you are saying things. All caps is like if you were shouting to the reader. Then what is the best font size? Well, it depends. General rule recommendation would be a font size of between 6 and 8 for footnotes, between 9 and 12 for text, but it depends a lot on the typeface that you're using and the intended use. And in your case, when you write papers, articles, and posters, you have constraints for that, right? You have the magazine, no, the editorial, yeah. You have constraints on what, you have actually templates on what font size and what typeface you should use. Well, I have to stop here. So, yeah, thank you. And let's go for the coffee break.